Heavy duty algebra day today, which I hope you are looking forward to. We are going to look at how to calculate what are called surface integrals. And I've got two very badly drawn pictures to try and show you two different situations. We'll look at this one first. This particular technique is for questions 1 to 4 on your homework. And this will be for questions 5 to 9. And they are quite different. You'll be able to tell just by looking at them, the way they're phrased, that they're obviously different. So here's the first one. Suppose you have a normal 3D function, right? So any given point on 3D space, there is a value associated at that point. Suppose we have a surface S described in this format, Z is X comma Y. So things like Z equals X squared plus Y squared, right? So that's like a hat. Not actually, it's an upturned hat, or whatever it might be. Z equals X squared minus Y squared, I think, is a cone, the surface of a cone. Then we have a thing called the surface integral, and it's a double integral over the surface of this function with respect to the surface. And this is the messy formula for it. That double integral, that surface integral, can be found by finding the double integral of this function, but you substitute the Z for xy. So up here, you see that the surface is going to be X squared plus Y squared or something. Then that's what goes instead of the Z's, followed by the square root of the derivative of this with respect to X squared, plus the derivative of this with respect to Y squared, plus 1 dA. And that double integral is a standard double integral over some region D with respect to an area. And dA is typically xy, or if the thing in the bottom is a circular, then you probably do polar. So I hide that one for a while. That is a double integral surface area. So here's our first example of that. This is like question 1. Suppose you've been asked to find this surface integral here, and it's going to be x, y, z, ds. What else are we told? We're told that z equals 1 plus 2x plus 3y, and that we're being told that it's going to be on this region here, on the ground. Right, this fella here is D. So can you imagine this very badly drawn picture represents this surface at this point here. So you got a big curved surface, but you just cut a little piece out of it, this little wobbly rectangle. If you project that down onto the floor, you see you could easily have a D. So D is the projection of the function, the surface, I should say, onto the XY plane, onto the floor. So we got the function. That guy there is basically fxyz. This guy here is the G guy. You plug and chug and you get a really messy algebra. So it's going to be the double integral of D of the function x, y, z. Square root of dg by dz squared plus a dg, so it's an x, dg by dy squared plus a 1 d and a. So it's going to be a double integral of x, y, replace the z with this fella. If you differentiate this guy with respect to x, you get 2, and then you square it. You do a partial derivative with respect to y, and you get 3, and then you square it, plus a 1. In this case, it looks to me like dy by dx would be reasonable. And when you see it written this way, that's basically telling you that x is between 0 and 6. And this piece is telling you that y is between 0 and 2. So that's how you read that notation. It's basically saying a little rectangle on the floor, x goes from 0 to 6, y goes 0 to 2. So since I'm doing the y's first, y's goes 0 to 2, and x goes 0 to 6. Okay, so we have x equals 0 to x equals 6, y equals 0 to y equals 2. This one here is nice and easy, isn't that? Just 9, 10, 14, the square root of 14, so I'll just stick it outside. And then you distribute the xy. Is it okay for me to dot that one? Because it'll take us forever in a day if we had to do it by hand. Are you quite happy about what this double integral would look like?
Yeah.
Yeah, okay, good. So that's an example of a surface integral. What in heck are we evaluating? Oh God. Can you imagine this green surface, right? This S surface. At every single point in that surface, isn't the function, this function, can't it be evaluated? So can you imagine that in every single point, there's a little number. Maybe that number is representing energy or temperature. So what you're basically doing is adding up all the energy on that plate. What's the total energy? Right? Or if each little point had a magnitude that was magnetism, it'd be the total magnetism, I guess you're finding. Okay, let's look at another one, a little bit trickier, but still in the same vein as question 1. So I guess I should keep question 1 handy. And this one is a bit like question 2. And this question, we're going to have a surface integral, that guy. And the function we're going to do it to is xz. And the surface is 2x plus 2y plus z equals 4. So a couple of issues here. The first issue is we need to find out what z is. That's not too bad. The second issue is going to be a bit trickier. We need to find d. Now, what do I know about this? It's this guy, oh, and it's in the first octant. So that's what we're told. Right, so I'll start off with, if 2x plus 2y plus z equals 4, would you agree it's not that difficult to find z? In fact, z then is that guy, right? So we got one of the pieces without really too much algebra. Now the second piece. Can you imagine this function, which is basically just a sloping plane in 3D? Can you imagine it being dropped down and hitting the first octant? And what would it look like? It would look like this. So if you look at 4 take away 2x take away 2y equaling 0, that's what it would look like when it hits the xy plane. Now that guy is basically a straight line. So let me figure out what the heck it looks like by rearranging it. How about 4 take away 2x is 2y. So 2 take away x is y, and because my brain can't handle it, y equals 2 minus x. So it's in the first octant, which means it can only live here, right? Only in the positives. And it's a straight line 2 minus x. So this is D. So a little bit more work. Now, how am I going to describe D then? Well, won't I just basically do, I think in this case, a typical vertical rectangle? And in this case, won't X go from 0 to 2? And won't Y go from 0 to 2 minus X? Does that seem like a reasonable way to describe this triangular region D? Now we have all the pieces. We know that the formula for the double integral surface integral, which is this guy, can become a double integral in D of x times z, which is this guy, times, differentiate this guy with respect to x, you get this number, differentiate it with respect to y, you get this number, plus 1. And I guess I shouldn't really have called that D. Shouldn't I have said x equals 0 to x equals 2, and I should have made this y equals 0 to y equals 2 minus x. And while I'm at it, shouldn't I call that dy dx? Right. So we are looking at an integral from 0 to y equals 0 to y equals 2 minus x. If you distribute this, you get 4x, take away 2x squared, take away 2xy. 4 plus 1 is 9. Square root of 9 is 3. I'll just stick it out there, then out the road. And are we okay now for me to ... that one? So it does have a lot more algebra, tweaking to do. You had to do a fair amount of work, didn't we, to figure out what D was in particular. Any questions so far? We comfortable with what we're doing up to this point? Now there are only 4. Good. Right, there are only 4 questions here, so it's not like you're going to get an awful lot of practice at these. But it's really dangerous for me to just randomly pick something. Because if I randomly pick something, can you imagine how ugly the square root thing could be? And then you end up with the problem of, yeah, we can set up the integral, but we don't know how to get it because it's too, it's too ugly. It's just not doable. So try and get as much practice as we can out in that. So where's my bits of paper? I don't know where I put them all. Right, that's this one. I'll keep this one for a while. This is question 3. I'm going to double into surface integral of, oh, good, x ds. And S is going to be a triangular region made up of the points 1, 0, 0, 0, negative 2, 0, and 0, 0, 6. We've got a big problem. I don't know who g of xy is. Great. How am I going to find it?
We work backwards. We find the equation of the triangle, then we find the equation of the line. We know that we set 0, the z to equal 0 in that situation.
Well, that'll get me the D. I agree. How am I going to get the Z?
Is it 1?
I'm not sure why you think it's 1. But There's nothing obvious in my brain that would make me think that. Z is going to be like 4x plus 2y minus 3z. Well, it won't be a z. Z is like 2x plus 4y minus 3. That's what z is going to be. Do you know if you pass a triangle through a plane, if you take a triangle and you pass a plane through it, basically that's what z is, that plane. That's what the problem is. Now, once I know what z is, I guess I can work on what this guy is. Have we got any suggestions to start the process? How do I get the equation of a point passing through 3 coordinate points? The equation of a plane passing through 3 coordinate points. Think Calc 3. I'm going to call the first one 1, 0, 0. I'm going to call the second one 0, negative 2, 0. I'm going to call the third one 0, 0, 6. I want the equation of a plane passing through those 3 points. I can't hear you, James. It looks like you're talking, but you ain't saying anything that I can hear. No. Your audio is not working, or at least I can't hear it. I will pretend I know what you're saying and I will put words in your mouth. So what you were going to tell me is that if you can imagine, this is just a visualization, that this might be the 3 points that they're talking about, right? Then can't I find the vector joining PQ and the vector joining PR? So let's do that. 0 take away 1, negative 2 take away 0, and 0 take away 0. Now I'll do PR. 0 take away 1, 0 take away 0, 6 take away 0. So I've just found the vector joining PQ and the vector joining PR. Now, if you want to find the equation of a plane, there's a formula, isn't there? It's the normal vector times x, y, z, right? It starts that way. The normal vector is the cross product of this guy and this guy. Basically, the cross product of those two guys, right? You can nod if that's what you were thinking, James. No nods, okay, you weren't thinking. Let's figure out what this is equal to. So many i's, take away so many j's, plus so many k's. If you cover this guy up, negative 12 take away 0. If you cover this guy up, negative 6 take away 0. And if you cover this guy up, 0 take away 2. And so I get negative 12 plus 6 and negative 2. And that's the normal vector.
Shouldn't it be positive 2? Because negative 1 times 2, or negative 2.
Oh, this one here? Let me check it. So it's this guy that goes here. 0 take away positive 2. Yeah.
Right.
It's worth checking.
Minus, though.
Yeah. We good? Right. This has been something that it may have been a long time since you've did it, but if you now know the normal, which is basically the vector that goes this way, you can get the equation by doing the dot product of the normal with x, y, z, and it will equal the normal times the position vector of any vector you like. I'm going to choose the position vector for P. And so it's going to be negative 12x plus 6y take away 2z is equal to negative 12 times that plus some zeros plus some more zeros. So it looks like it's negative 12x add 6y take away 2z. That's going to be add 12x but subtract 6y. Divide everybody by negative 2. That was a lot of work just to find the equation of the points that go through this triangle. So far, so good. Now, what does this fella look like when he hits the floor? Because that's going to be my D. 1, 0, 0. That will become 1, 0. Agreed? 0, negative 2, 0. That will become 0, negative 2. And 0, 0, 6 will become the origin. Do you see how I found D? I looked at these 3 points in X, Y, Z, and I just basically made the Z disappear, and what's left is the X and Y coordinates of what that triangle looks like. It looks like this guy.
Could you move your paper up a little bit?
Does that help?
Yeah, thank you.
I'm more interested in, do you understand what the process is rather than just a specific example? I think it's living up to the expectation I gave that there's going to be some heavy duty algebra going on here, right? There's how to find the equation of a plane in 3D. I haven't seen that for donkey's ages. Right, I need to get the equation of that straight line, don't I? What's the slope of that line? Should be able to tell just by rise over run.
Positive 2.
Right. And would you agree it crosses the y-axis at negative 2? So there's the equation. So when I'm putting in my little vertical rectangle, I can do the x's going from 0 to 1, and I can do the y's going from 0 to 2x minus 2, which is nice. So moving, I need this guy, so I'll write him down up here. Right, that's the guy that we're going to be doing. It's going to be the double integral over d, which is going to be from x equals 0 to x equals 1. It's going to be from y equals 0 to y equals 2x minus 2. X is good. The square root of, well, if you differentiate.
Wouldn't the y values be from 2x minus 2 to 0?
A very interesting question. I'll just say swap. Nah, it's too messy. Yep, I would agree with you. Because when you go from a negative number to a positive number, and technically won't that be negative because it's lower down. Okay, differentiate this guy with respect to x, and then you square it, so you get negative 6. Differentiate this guy with respect to y, and then you square it, plus 1. So it's going to be the integral from 0 to 1, from 2x take away 2 to 0, 36, 46, and x. I'll dot it, right? I guess I could have pulled out the square root of 46, but that's about all. Are we good with that question? So here's your chance to ask if you're not sure of any of the steps that I put you through.
Who wants to take attendance?
Good idea. Let's take attendance. I'll give you a few moments to think about it, and then we'll move on to the last example of this type of surface area. There are two, but this is the first one. Okay, there's 27, so 3 missing. Let's continue. The last one, most of the messy stuff has been done. They're going to tell you Z, so I don't need to figure it out. And they're going to tell you D, so I don't need to figure it out. So what's the problem? This is the problem. We are being told that Z is this massively ugly fractional combination of X's and Y's. And the region D is really nice. So it's ugly with nice. I guess that's something. Now that makes this guy the g of xy. So it's going to be this surface integral. It's going to be from, there are a lot of symmetry here, I guess it doesn't matter. Let's do x's first. I haven't done x's first for ages. And it's going to be y. I guess I'm going to have to write it this way just to make it a little bit easier to differentiate. Okay, if you differentiate this guy with respect to x, you multiply by the power, reduce it by 1, you get x to the half squared. And then you get y to the half squared. So we've got the integral from 0 to 1, from 0 to 4, y times the square root of x plus y dx dy. Okay. I need to get this fella with respect to x. That guy is really a constant, so I don't care what he is, he's just y. I got to figure out how to deal with the square root of x plus y, what it is, integral is in terms of x.
Mr. Robertson, you did get +1.
Oh, thank you. I need to figure out what this is, integral with respect to x. Okay. If I call it x plus 1, y plus 1 to the half, can you see that where I'm leading is, this is in fact a basic power rule, really. So when you add 1 to the power, Divide by the new power. And you might think, well, what about x plus y plus 1? The good news is that if you do that, don't you differentiate that with respect to x? And isn't the answer 1, so it doesn't really do anything. So we now have 2/3 x plus y plus 1 to the 3/2, and we plug in these numbers and we'll see what we get. If you plug in 4, your x plus y, well, you don't. You get 5 plus y 3/2. And if you plug in 0, you get 1 plus y to 3/2 dy. I'm going to split this into 2 separate questions. I'll pull out the 2/3 because it's annoying. So I'm going to find that answer, and then I'm going to subtract the answer. Okay, I need some help here. How on earth am I going to integrate that?
Integration by parts.
Who are you going to make F? Who are you going to make G? I like it. It'll work. So it's not that I'm saying that to throw you. But you have to choose an F, and don't you have to choose a G?
DF would be the second one.
Oh, you're a UDV person. Okay, yes, that'll work. And same idea over here, right? Nothing wrong with that. It wasn't the way my brain was thinking, but the minute you said it, I know it would work. Alternate method that would also work. Not saying this one's better. Not saying it's worse, just different. Any suggestions? U-subs. Now you may think, how's that going to work out? Well, let's try it and show you. You get 1. So du equals dy, that's not a big deal. That's kind of nice. Something ugly is going to happen. Do you see that you've got an orphan y left over? Don't I need to convert that y into u so that we can continue? And all I've got is this to work with. Yeah. So the y will be u minus 5, u to 3/2 du. Add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. They can't be both that. Darn it, nobody caught me. That's 5 halves. So that becomes 7 halves. So that becomes 2 sevenths. And that's 7 halves. Evaluated at y equals 0 and y equals 1 and ... All right, now I've seen that being written down, I think integration by parts would be quicker. Because you still have to do a similar one and then combine the two answers. So some really heavy duty algebra. Each one had its own little hiccup. This one here, the integration is where the problem was. The start was pretty clean and the end was not. I'm going to bring this page back in a minute. So I just want to show you the second half that we're really just going to do an intro to. We are going to find what's called a flux, F-L-U-X. And here is some definitions of what the heck it is. So when you do it's a version of a surface integral essentially, but it's a version that's called the flux. You will be able to find this. So none of these make particularly sense to me. But then again, I'm not a physics engineer, so here goes. Flux describes any effect that appears to pass through or travel, whether it actually moves or not, through a surface. I'll use that version. A flux is a concept in applied maths and vector calculus, of course it is, which many applications to physics. Evidently, flux is a vector quantity and in some cases describe the magnitude and direction of the flow of a substance or property. In vector calculus, flux is a scalar quantity. So we have a number, but it comes from a vector. And evidently, here are lots of examples of flux. Did you know that luminosity, which I'm assuming just means how much light is emanating from a surface, is connected to the flux? The electric flux, whatever the heck that is, magnetic flux. And transport phenomena is heat transfer, and you can also use it in fluid dynamics. So if you're anything like me, you're not that bit interested in anything I just said in the last 5 minutes, but I'm going to be selling it on why we can calculate, or why we would want to calculate a thing called flux. So it has a formula and it has a notation. And its notation, let me see, I've already got my page written down for it. It's coming up now. This guy here. You can use surface integrals to evaluate flux. So I want you to think of your vector function f as being made up of p, q, and r. When they ask you to find the double integral of f dot ds, that is what flux is. That's how they describe it as a mathematical thing. It's a double integral, surface integral, of a vector function f with respect to a surface vector s. We reduce that to the classic double integral with d. Remember, d is going to be what that surface looks like when you project it onto the floor. Right, so your surface may be up here, but when you look at it on the floor, you get a rectangle, a circle, or some region. That's what d is. Now, it's made up of this weird formula. Negative p dg by dx, take away q dg by dy, plus r dA. P, q, and r are functions of essentially x and y and z. G is the surface, so every one of these z's here gets replaced by an xy. And God in Himmel, is that not one ugly looking thing to deal with? Because what you're going to have to do is you're going to have a function with x, y's, and z's here, here, and here. All the z's are going to get replaced by g of xy, right, whatever the equation of the surface is. And if that's not bad enough, you then have to stick a p, a q, and an r, and a couple of derivatives in front of it. And that's only to get to the point where you have a double integral that you can calculate. So can you imagine this green thing is the surface? At every point on that surface, there is a vector function leaving it, right? Something's passing through that surface going in that direction, and then something else is going through that direction. Now, passing through could be leaving it as well. Couldn't it just be points of light leaving it, in which case the flux would be the luminosity? But couldn't that also be something to do with electricity? So I guess that's why it's called electric flux. Couldn't it be magnetism or gravitation or something that has a direction and a magnitude that's on that surface, either leaving it or coming in towards it? I guess you could have things entering a surface as well as leaving it. And the flux is basically the average value per square unit in this case. And that happens in questions 5 up to question 9. So I think I've got time to set up question 5 to show you what the darn thing looks like. Well, here is calculate the flux. The vector function f is given as xy, yz, zx. The surface in this question is being described by that guy, which is basically a hat coming down the way. And D is given to us directly, so we don't even need to calculate it. It's that guy. So can you imagine that is what the surface looks like? It's like a hat. Can you imagine they took a little rectangle here, projected it up, and you'd have a kind of little curved bit on the hat. That's what S looks like. Not an artist. So I should be able to put this package together, shouldn't we? So this fella is D, which is from x equals 0 to x equals 1, from y equals 0 to y equals 1, that's D taken care of. Negative P, which is negative this guy, times the derivative of this guy with respect to x, which is negative 2x. That's where this one comes from. Take away Q, which is this guy, times the derivative of G with respect to y. And if you do that, you get negative 2y. And then you add an R, which means you add a zx. And then you do your dy dx. Have you noticed that this integral still has z's in it? Those z's are going to get replaced by that. So it's going to be that times that is positive 2x squared y. That times that is plus 2y squared, but instead of z, you get that. And this guy that says zx is basically going to be this guy, x dy dx. God, that's tight. Okay, I'm ready for a dot, dot, dot. Can you imagine multiplying that whole lot out, maybe getting lucky and collecting some like terms, but probably not? Won't you then just do a dy dx on it and it'll be power rule in the usual way? And the answer you'll get is 42, which could mean that the luminosity on that surface is 42 lumens per square inch, or whatever the units happen to be. And if it was a magnetic story, I guess you'd get 42, whatever the units of magnetism are. That is one, I don't know, that's kind of algebraically one kind of cool question. Even if I